Previously, when we talked about parallel lines, we focused on the relationship of the angles created by the lines, that alternate interior angles were created by transversals crossing parallel lines, and that those alternate interior angles were congruent, that corresponding angles were congruent, etc. Now we are going to use similar triangles and the triangle proportionality theorem specifically to talk about the relationship of the segments of transversals that are cut by parallel lines. And this is going to end up in something that we often call the generalized or the strong three parallel line postulate. And so, as a quick reminder, the triangle proportionality theorem tells us that when a line parallel to the side of a triangle intersects the other two sides, it divides those sides proportionally. Specifically, in this case, from the video on triangle proportionality theorem, we know that bx over ax is the same as by over cy. And that rather than have to worry about the complete side lengths of similar triangles when they are nested into each other like this, we can also use the same proportional relationship with the segments of the sides that are created. We're going to extend this idea into the strong three parallel line postulate, which says that if two or more transversals are cut by three or more parallel lines, then they are cut into proportional segments. So for transversals A, B, and C here, or ABC and DEF, we know that AB over BC is equal to DE over EF. Go ahead, pause the video, write down the statement of the three parallel line postulate, the strong three parallel line postulate, as well as the diagram and the ratio that we're going to look to prove. Come back when you are ready to see the proof and then see an example of how this works. So if we are going to put the strong three parallel line postulate into the statement of a proof, we would say that given that lines L, M, and N are parallel, and that AC and DF are transversals of L, M, and N, which we don't actually need to state in our given, we want to know that the ratio of AB to BC is the same as the ratio of DE to EF. That is the provable statement that we're going to use to actually go through the proof of the three parallel line postulate. Well, in the setup that we have right now, we don't have a whole lot that we're able to use. But one of the things that we can do, and that we've seen through the course of the course, that we can do in proofs is we can construct things on top of the diagrams that were given. So in this case, we can add another transversal. This one going from D to C and intersecting line M at point G. And the reason that we do this is because now we have triangles that we can talk about, and we can jump backwards and use the triangle proportionality theorem. We have triangle ACD and we have triangle CDF, each of which are cut by parallel line M so that AC, CD, and DF are cut into segments by lines that are parallel to the bases of those triangles, which allow us to use the triangle proportionality theorem. Now, if you would like to go ahead and see what you can do about proving this on your own, go ahead, pause the video, see what you can do about this proof. If you get to the end, that's great. If you find yourself stuck at some point, that's totally okay too. So if you want to prove the video, stop the video and see if you can prove this on your own, go ahead and do that now. If you want to just keep watching and see the proof for yourself, that is totally fine too. We'll get started with the proof here in just a minute. So as I create the proof here in our two columns, I'm going to sort of wave my hand and say the top line of this proof is the given, that L, M, and N are parallel. Because that's the case, we know that we have triangle ACD, and the triangle proportionality theorem tells us that the ratio of AB to BC is the same as the ratio of DG to GC. And that is because of the triangle proportionality theorem. And that's what we get with triangle ACD. Well, in triangle CDF, we also have GE and CF being parallel to each other. So the ratio of DG to GC is going to be the same as the ratio of DE to EF. That is also because of the triangle proportionality theorem. Notice that once we draw the transversal DC on top of the diagram, we can take a step in the proof before talking about the triangle proportionality theorem here to say that DC is a transversal, and we would just call that by construction as we did before. But because we have added it to the diagram here that we are using as part of the proof of the three parallel line postulate, we can see that it's there and we can refer to it because it's there. What we would need to do, though, is if we wanted to, say, drop a perpendicular line from A, we would need to show that that is by construction because we have something that is specifically related to it, that is perpendicular to L, M, and N. But in this case, because it is just adding that extra transversal, we don't necessarily need to add it, but we can do this here for the sake of completeness. And that would go up at the top of our proof after our given. Well, now we actually have everything we need to know in order to be able to prove the three parallel line postulate. We have AB is equal to dG over GC, and we have dG over GC is equal to dE over EF. Well, because we have all of those ratios equal to each other, we know that AB over BC must be equal to dE over EF, and that is because of the transitive property of equality. So not a terribly long proof, a relatively straightforward one once we add the extra transversal to create triangles ACD and FDC. So that is the proof of the strong three parallel line postulate. Let's take a look at a real easy quick example of what that means in practice. So here we have again lines LM and N that are cut by transversals ABC and DEF. And if we know that the length of AB is 4 and the length of BC is 1.5 and the length of DE is 3, we can use that to calculate the length of EF. Again, if you would like to attempt this problem on your own, go ahead, pause the video and work on it now. Otherwise, you can just stay on the video here for a second and we will do it together. So if we substitute the values that we know directly into the ratio statement of the three parallel line postulate, AB over BC is 4 over 1.5. dE over EF is 3 over x. Taking cross products here gives us 4x is equal to 4.5, which therefore means that x is equal to 1.125. So that's it. That is what we call the strong three parallel line postulate. We will see later why it is called strong. There is another version called the weak three parallel line postulate. But again, it says that if two or more transversals are cut by three or more parallel lines, then those transversals are cut into proportional segments.